Hello, my name is John. Thanks for stopping by. Today I want to present a new theory on what light is. And of course I hope you'll follow along and find some interest in it. Most people interested in the study of light have a tendency to lump all visible light spectrums into the same category, simply called light. And so often you'll see them explore the subject with the question, what is light? But Richter's theory makes a more pronounced distinction of light by asking, what is starlight? It's possibly a bigger difference than most currently accepted theories include in their calculations, and hopefully by the end of this video you will either agree with me or at least agree that the logic behind the theory has some merit. Einstein and other early 20th century pioneers used starlight to come to their conclusions about photons, or the notion that light has mass we commonly refer to as particle theory, and so Richter's theory of light follows that same starlight precedent. To start answering the question, we need three things: a star, or the sun, something to see, like these rocks, and something to see with, your eyes. Before we get into Richter's new theory, we should briefly touch on the current and most accepted theory on light. The only thing I ask while we go over this section is to keep in mind that this is not my theory. One concept that is highly regarded amongst several different camps is that light has a dual nature. They believe that light is both a particle of mass but also an electromagnetic wave. Here is an analogy. Just as oxygen and hydrogen are physical atoms in the air, they also act as physical members of a sound wave, which enters our ears. Sound waves are caused by compression of those atoms and molecules in different frequencies. Some of those frequencies the human ear can hear. Believers of light duality somehow extrapolate the notion that these particles of light come in different compactions or different wavelengths that the human eye can then send to the brain to be interpreted as light. The current prevalent theory states that these particles and waves travel down together from the sun onto items like these rocks, and then reflect off of those items into your eyes. And now for the Richter theory, which agrees that all starlight is comprised of particles. The sun emits particles just as any radiative or radioactive material does. One main difference between the Richter theory and the most common prevalent theory, though, is that the Richter theory does not believe the particles reflect off of items of physical mass like these rocks. I believe the particles pass straight through the rocks and down into the Earth's crust as far as they can go before friction stops them. In short, these emissive particles do not reflect off of mass, but rather they enter the Earth's crust in a straight line. Interestingly, I personally believe these collected particles energize the Earth's crust and accumulate there, using the Earth's crust as sort of an electromagnetic condenser or capacitor, which might give us an explanation of origin for gravity and the Earth's magnetic field. That's called Richter's theory of gravity, and it's a video for another day. So the question remains, how do we know that the emissive particles don't reflect off of the rocks? And the answer is simple. It would make us blinder than bats just as surely as we were to stare directly at the sun. The delicate tissues in the retina cannot withstand any bombardment of emissive particles. It would be bad. Don't try this at home. And the next logical question is, well, then how do our eyes see the rock? This is where the particles come into play. As these fast-moving particles slam into the surface of the rock, there is an energy created by micromechanical friction, which then causes the outer surface of the mass to generate its own electromagnetic waves which the eye can see. Of course, all mass, atoms, conglomerates of atoms and molecules are going to have different wavelengths of light. They create it themselves. But that's not all. The particles which pass through the rock, say in the middle of the rock where we can't see, also generate electromagnetic waves. But those waves cannot pass through solid objects like the rock itself, so we only see the waves generated by the surface of the rock. It's not necessarily important to know for eyesight. However, in short, it means electromagnetic waves are being generated throughout the entire thickness of the rock. And that has its own possibilities for future adaptations of energy from electromagnetic waves. Another good thing about these EM waves are that we can look at them all day without injuring our eyes. There's no particulate matter in waves that enter our eyes. But what about moonlight? If moonlight has no emissive particles, then how does it cause the rocks to emit waves? It doesn't. Unlike particles, electromagnetic waves can reflect off of mass items like these rocks. So when you see the rocks at night, you are seeing them from reflected moonlight, which is why they lack the color they would normally emit during the day. The eye's retinas have special sensors called rods and cones to detect different kinds of light waves, which also accounts for the lack of strong color in reflected moonlight off of the rocks. The takeaway here is that sunlight particles do not reflect off of mass, but electromagnetic waves can reflect. In fact, that's how radar works. The radar tower sends out electromagnetic waves, and any objects in their path reflect some of those waves back to the tower. But what about stealth planes? They don't reflect waves back to the tower. Precisely. They are designed to reflect the waves away from the tower because they are angular, like the rocks. But wait, if the rocks are angular like the stealth plane, then how do they reflect EM waves to our eyes? The simple answer is that we can't see the reflected moonlight waves being reflected from the rock, at least not all of them. But we do get a few of them, those that are angled toward us. And this is why night vision is a lot different than day vision. Have you ever noticed that at night in the moonlight, it takes a second or so for objects in the distance to come into focus? That's because the thing you're looking at is not creating its own EM waves, but rather only reflecting some of the moonlight beams towards you. And although it doesn't reflect all of the moonlight to you, it does reflect enough for your brain to extrapolate. So your brain is only getting a partial picture of what you're seeing, and the incredible brain then takes these partial wave data and fills in the rest of us, kind of giving us a picture of what it thinks we're looking at. Unfortunately, that's why we're so susceptible to optical illusions. The human brain has a tendency to fill in for missing data. In the image, you should see an elephant. If you focus above the elephant's eyes, shoulders, and hips along its back, it should look like a normal elephant. But if you then change your focus down toward its feet, you will see that it has 5 of them. The reason this is true is that the rods in the periphery of the retina sends data to the brain, and that data can be corrected by the brain or changed to something that would be normal, while the data coming from the focus center of the retina, from the sensors called cones, are not as susceptible to being manipulated or changed by the brain's ability to normalize things. In short, these illusions occur because humans evolved to have vision at night, which is not complete vision, and the brain needs to fill in things for us to have a better understanding of our surroundings. Here's a bonus mind boggler. Starlight, including sunlight, is not light at all. We cannot see star or sun rays because they do not have electromagnetic waves. We can only see the excited gaseous particles between our eyes and the star. The gaseous particles are emitting light waves, not the star. The star is emitting radiative particles, which excite those gases, but we cannot see the particles. If we could see photon particles, then they would be the only thing we could see, because they are all around us, all the time, not only coming from stars or the sun, but in Richter's capacitive theory of gravity, photons are also the particles which create the Earth's magnetic field, which are flowing in and around the Earth, looping at the speed of light constantly. But again, that's another video. Again, the takeaway is simply that if we could see photons, the only thing we would see is just a blank white canvas. Lastly, photons, or emissive particles from the stars and sun, do not travel indefinitely. You can stare at the stars all night long without hurting your retinas, so that's obvious. Ergo, the star's emissive particles are not reaching us. They have stopped before reaching the Earth, except for the sun. Perhaps they slowed and stopped. Perhaps some other gravity field, like another solar system or large planets, pulled them away from their path to us. But we're certain that those photons from faraway stars did not reach us. The only thing we can see of distant stars is simply the excited gas compounds that were excited by those faraway photons, which is amazing, because that means that although the emissive particles from the star themselves are not able to reach Earth, and that is probably due to gravitational pull from other solar systems or bodies, defining the very mass of photons, and that being affected by gravity proves they are indeed particulate mass. But it also means that electromagnetic waves, at least in the visible light spectrum, are capable of traveling hundreds of millions of light years. Truly awesome.